Hello there, and welcome back to our exploration of the internals of B+Trees. So the leaf nodes already had their time in the sun. Let's now switch and talk about the inner nodes of such a B+Tree. These inner nodes are part of a search tree structure, and as such they are vital in guiding our search to the leaf node sequence set chain. One could ask yourself, hey, if there is already the sequence set chain and the entries in that sequence set chain are already ordered, that's very useful because we could just use binary search. We could binary search on the entries inside that sequence set chain. Say you are giving some key value that you are looking for regarding your query. So for example, a key value k equals 42. Okay, then, we could just use binary search to locate that 42 among the sequence set of ordered key values ki that we find if we look inside the leaf level of our B+Tree. Okay, but this is actually a strategy that's doomed to fail because if we would perform such a binary search, we would have to inspect this many keys. Why is that? Because each row in table T, and T has actually that many rows, each row in table T would be represented with its index entry inside the sequence set. A binary search across this sequence set would need to expect this many keys. So the logarithm base 2 of the cardinality of table 2, that would be the number of keys that we would need to inspect. That can be quite a number of keys if T is large. But the news is even worse because binary search is a process in which we are guided, inside this ordered sequence of keys from one end of the sequence to another. Binary search is based on jumping around in that sequence. You would identify a pivot and would find that your key is larger than that particular pivot. So you would look to the right of this particular pivot and then look there, and would then further be guided to look there and then to look there and to look there. You would have to jump around in that particular sequence in a rather unpredictable fashion. You could not tell beforehand where such a comparison with a pivot will lead you, to the left or the right inside the sequence. So it's an unpredictable sequence of I/O operation that you would face, and that's what defines random I/O, which deserves a thumbs down in our context. As you know, random I/O on the pages of our secondary storage, in this case of the pages of the sequence set, is rather something that we would like to avoid. Also, if we are loading such a sequence set page during that binary search, we would use it to inspect a single key, the pivot key, the current pivot key in this leaf page, only to then decide that, okay, this is all we need to do, or this all we had to look up in this particular page, throw it away and move on with the search to some other, probably far away page in the sequence set. That's also very bad. This means that we need to inspect as many pages as we need to inspect keys during this binary search, and this means lots of I/O in random fashion. This is something that we rather try to avoid. And B+Trees avoid that with the help of the search tree structure that is erected on top of the sequential sequence set. What we find there is an n-ary search tree structure with n large. We hope that the large node sizes of 8 kilobytes allow us to store many keys and then thus many pointers to subordinate search trees inside a single node. So let's zoom inside one such inner node in a B+Tree. And again, this entire thing would be an 8 kilobyte page. All right, just mentioned in passing, also these inner nodes are connected to each other via next and previous pointers. Okay, so there is indeed a chain of nodes, of inner nodes that are on the same height, on the same level inside the B+Tree. This can also be useful to support update operations inside the B+Tree. We will briefly touch on that later on, but otherwise we will largely ignore these sequence set or these next previous pointers on the levels of the inner nodes. They are of course crucial in the sequence set on the leaf level. Okay, so what do we find inside these 8 kilobytes? We find index entries. So this would be one index entry. It's again a pair of a key value and a pointer. Okay, the pointer in this case is not pointing to particular rows in the heap file, but it's pointing to a search subtree, All right. So what we will find here is either another inner node or maybe the leaf node of the B+Tree that we are currently navigating. Okay, but we are not pointing to the data file here. This is an inner node. All right. What will we find inside the subtree? Well, you can see the semantics of that search subtree provided here at the bottom. Okay. The values inside this subtree, the values that are represented in this search subtree, their A values lie between K1 and K2, which are just the key values that frame this pointer inside the inner node. So K1 is here, K2 is here. In the middle, we've got this pointer pointing to a search subtree in which all entries lie between K1 inclusive and K2 exclusive. All right, so this is the semantics of the pointer that is associated with K1 here. Okay, and it's like that for all the other entries, that you find here in this inner node. To the left of K1, there's another pointer, the P0 pointer, pointing to a search subtree in which all values are less than K1. Okay, and that would conclude the pointers to all the search subtrees here. Okay, you see that I've indicated that this particular node has 2 O entries. So this is the first entry, this is the second entry, this is entry number 2O. Okay, 2O is a special number. Actually, it's related to O, which is called the B-tree order. I will come back to the B-tree order and the meaning of the parameter O on the next slide. Okay, but in this schematic, all of the index entries of this inner node have been occupied, and the maximum number of entries inside such an inner node is 2O, plus the P0 pointer that points to all entries that are less than K1. And this is, of course, a search tree structure, because the K1, K2, because these key values are indeed ordered, we can again use binary search very efficiently on the key values inside this inner node to quickly identify the subtree that we have to descend into to find the key value 42 maybe that we are looking for. Okay, so this is really a regular search tree structure whose order on keys here it supports an efficient binary search that we can use inside the inner node. Okay, these key values, this value, and this value, these are called the separators because they are separating the entries in the subtrees that are separated by these key values. Everything to the left of this K1 value is less than K1. Everything to the right of this K1 value will be K1 or larger. Everything to the left of K2 value is less than K2. Everything to the right of K2 value is K2 or larger. So this separates the entries of table T into different search subtrees here. That's where the name separator comes from. Okay, some more notes on these inner subtrees, on these inner nodes, I'm sorry, before we switch over to the terminal again and then see how that indeed looks like inside PostgreSQL itself. Okay, so let's first talk about this O parameter. This is related to space usage in the nodes of a B+Tree, in particular of the inner nodes at this point. All right, so the B+Tree tries to use space in an economically fashion. So we won't allocate 8 kilobyte pages. Nodes in a B+Tree are allocated in 8 kilobyte granularity. We won't allocate such a node without really using it to a useful degree. And the useful degree is defined by this parameter O. Well, if the maximum number of entries, inside such inner node is 2O, then O, that is the half the number of entries is defined O, and this is the order of the B+Tree. Okay. The B+Tree maintenance routines, node insertion, node deletion, or entry deletion, entry insertion, they all make sure that all inner nodes carry at least O, the order of the B+Tree, at least O entries, and at most, of course, 2 O entries. No B+Tree will be less full, B+Tree node will be less full than 50%. O represents 50%, 2O represents 100%. Indeed, we find that the typical degree of occupancy inside such a inner B+Tree node is about 67 to 70%, which lies between O and 2O. Okay. Well, of course, it would be beneficial to always pack these inner B+Tree nodes to their maximum occupancy, so to the 2O with 2O index entries. Actually, this 2O is also called the fan out of the tree. This is the maximum number of pointers that can point outside such an inner node to more subordinate subtrees. It could be beneficial to actually pack these B+Tree nodes to their maximum degree. But as we will see when we talk about B+Tree maintenance, it's really very useful to have some slack space, to have some space, wiggle room inside these nodes to move entries from one node to another. We can benefit from free space that is present in some of these nodes, but the order O of a B+Tree controls that we never store less than O entries inside a B+Tree nodes. So having wiggle room and some slack space is nice, but not too much. We would otherwise waste node space and allocate more pages for the B+Tree than actually would be necessary. Okay, so as I told you, we would use binary search inside the inner tree and inside the inner nodes to quickly locate the B+Tree subtree, the sub-search tree that we want to dive into. And of course, the search would start at the root, and we would be guided by the separators and their associated pointers into lower levels and lower levels of the subtree. Since this is the balanced subtree, all of the paths from the root to all the leaf nodes are of the same length, or all of the subtrees that you've seen on the previous slide here are actually of the same height, which would be the equivalent statement here. So all of these subtrees are of equivalent height, regardless of which k value I'm actually looking for, regardless of which pointer I'm following. I will end up in a subtree of equal height, and thus the length of the path, the length of the way from the root to the leaves inside such a subtree is really predictable. It's the same length for all of the entries, the leaf entries that are stored in the B+Tree. Okay, so how long would such a path be? That's a quite interesting question, because each such step in a path would mean to access the next inner node, or at the very end, the next leaf node inside the B+Tree. And accessing a node means loading a page from secondary storage if it's not already present in the buffer cache. So it really makes sense to take a quick minute and try to get an impression of how long will the path be in such search trees, in these B+ search trees. Okay. If we for now assume that these B+ trees really are used to their maximum degree, to the fan out, to the 2O degree, all right, then this would be the observation that we could make. We would, any search would start in a B+ tree at the B+ tree root, which represents the entire contents of the base table. So the root of the B+ tree represents this many entries. When we, from the root node, which is just another inner node, from that root node, if we follow a pointer into a search subtree, then this would be one of F subtrees that we have selected. One of F subtrees. The search space that we are now looking at, the number of rows that are represented by this particular subtree is 1 divided by F, or 1 over F times T. Okay, so stepping down in the path in the B+ tree from the root to the first child node of the root would reduce the search space to this size. Stepping down another step from that first child to the next grandchild would reduce the search space by another factor of 1 over F. We would continue to do that. We would continue with each step downwards the tree. We would reduce the size of the search space until we have reduced the search of the search space to a single entry. That particular entry in a leaf node that we were hunting for and whose RID we will dereference to find the wanted record inside the data file. All right. So one could ask, how many times do I have to reduce the search space size by a factor of F until I reach a single entry in the leaf level? If that would be as times, if that reduction would happen as times, then as is exactly that. It's the logarithm to the base of the fan out, the base of F, over all the entries inside that B+ tree. All right. So what would be typical values? What would be typical values in real B+ trees out there? How deep would these trees be? How large would S be? How many steps would we have to undertake from the root downwards to the leaves? It really is a crucial performance parameter for our B+ trees. So let's see. If can you see that? Yes. So if the page size is 8 kilobytes, okay, this is what we were assuming all the time, and the index entry size, one index entry is a separator value plus a RID, and that would be 16 bytes in PostgreSQL. So that would be the key and the separator and the page pointer. Okay, so what would that mean? What would that mean for the typical fan out? Okay, the typical fan out F that we would see. I think it would be around 500. Since 500 times the 16 bytes that each index entry would require, plus some, say, metadata, the size of some metadata here. That would be about 8 kilobytes. So that would be the fan out that our B+ tree could support. All right. So now let's see if If we are looking at tables T of, say, 1 million entries, this would be like the index table that we have used so many times already in the last terminal session with PostgreSQL, and that we will use again in a few minutes. And if F is 500, so that would be the maximal occupancy in all the inner nodes. This is really the maximum that our B+Tree could hold, and that would lead to the shortest path. Then we would have as would be the logarithm to the base of 500 of 1 million. And that's about 2.2. Okay, so 2.2, this would be the expected length of a path from the root to any leaf entry inside my B+Tree. So this is really a very shallow tree. The depth of the tree is only about 2. So a very shallow tree, but a very wide tree with a fan out, so a number of pointers, child pointers going out of a maximum occupied inner node of 500. So these B+Trees are really rather shallow, to depth 2 only here, and they are really wide in a sense. So let's see what that means if we have a billion rows inside this table. We are working with the same fan out. Then the same fan out over a billion rows would lead to a size of 3.3. So these, I would consider such a table a really large table already. I would consider this the good case. If all of the inner nodes in our tree are really fully occupied, then that would be the fan out. Indeed, the fan out would be probably a bit smaller, like only 70% of that. In a typical B tree or B+Tree, but that would be in the range of depth 3. That would be in the range of depth 3 only. So even if we are indexing really super large tables, we can expect rather shallow trees. And path length of 3 means it's only 3 IOs that we will perform on our way down from the root towards the leaf level of this B+Tree. I consider that good news. Okay, so I think it's now time to switch back to the terminal. There we are. Okay, let me take a sip of coffee here because I have a rough voice. Okay, excuse me. Okay, so yeah, let's see. Let's see whether we can actually find the structure of these inner nodes inside PostgreSQL, and let's also see whether we can replay such a descent from the root of the B+Tree towards the leaf level. Let's see whether we can find our way through the data structure that PostgreSQL has provided for us, now that we know how the data structure internally is to be interpreted. So let's start at the root level then. And the page inspect extension has a special built-in function for us, the bt_meta page function, that gives us information about the B tree itself, but also about its root node. Where can you locate the root node among the 2,745 pages that make up the entire B+Tree? Let's see what we find there. Okay. So the root node is located in this particular page. So in a second, we will use this 412 to access this particular page of the B+Tree. It's located at level 2. So if you recall, all the leaf levels were the leaf nodes were located at level 0. The root is located at level 2. This is the B+Tree of depth 2, which is to be expected, I would say. It's a B+Tree over 1 million entries, 1 million rows, and our back of the envelope computation on the piece of paper just told us that this is the expected depth of a B+Tree over a table of that size. Okay, I think that makes sense. So let's access the page 412 that holds the information about the root node. Let's switch to vertical display for that. Okay, so that would be some summary information about node 412, which is the root node of our B+Tree. And indeed, its type is indicated as R, which means this is a root node. Okay, there would only be one node indicated with type R in the entire B+Tree, of course. Okay, live items is 10. That means that there is 10 index entries inside this root node. And so 10 pointers are pointing to 10 different search subtrees below that root node. This is what we find there. The root node page itself is 8 kilobytes large, as we've already found. It has no previous and no next nodes on its level. Well, that's no surprise because this is the root node. It's really special. There is no other, no other root node on level 0. Okay. Everything else is expected. BTPO is indeed the level of the node. Again, it's at level 2. We knew that already. So, all right. Very nice. So, let's now look at the entries. Let's now look at the entries, the index entries themselves that are located and stored inside the root node. Okay, let's see. So we are looking at the actual index entries inside page 412, which is the root page. 10 entries there. Okay, that's what we expected. Okay, this entry, there's 10 entries there, but one of the entries looks a bit different than the others. It's also only half the size. This is the P0 page pointer. If you recall, let's switch back to the slide for a minute. This is the P0 pointer, this pointer. It's just a pointer to a page that holds the root of this subtree. All right, no key is associated with P0. This K1 key is associated with P1. This is one entry. The P0 pointer is standing there on its own. Okay, and that's indeed what we find here in our implementation inside PostgreSQL. This is just the P0 pointer. 8 bytes are sufficient to store that, and it's pointing to a node on level 1 of the B+Tree that is held in page 3. Okay, so here's some other entries. This is the next entry, the next index entry inside that root node, and it's a regular entry that consists of a key value and a pointer to a page, which will hold an inner node at level 1. All right, so here's another entry and so on. There's another 9 such entries to be found inside our root node. Okay, so let's not forget the 411 here, because that will be the next inner node that we will visit when we descend into the B+Tree on our journey here from the root towards the leaf level. Let's decode the key values first, because these key values inform us about the expected A values, the key values that we will find represented by this subtree with the that is represented by the page 411 or the 411. I'm sorry, or the node 411. So let's use SQL itself again to decode that value. That's hexadecimal, and it's 0197 9777. Okay, and 032 EED. If I'm not mistaken, let me check that. 032 EED. All right. Okay, so these are the K1 and K2 separator values that we have seen on the slide. Okay, so this is a separator that separates the values in the subtree pointed to by P0 from those pointed to by this first index entry. This first index entry points to a subtree in which the values, the key values that are represented, lie between this 104311 and inclusive and exclusive 208621. All right. So this is the key range, the range of A values that is represented by the subtree rooted at page or at node 411. Okay, so if you look at these inner nodes, you can disregard these slot pointers here. So we are only interested in the pages here. These are pages inside the index file, the roots of the subtrees that are being pointed to. These slot numbers are unused in this case. So these are row IDs or CT IDs, but please disregard the zeros and the ones here that you see. The only interesting information is the page number that we have found here. All right. And here you can indeed see the 16 bytes of index entry size that we have assumed as we made the back of the envelope computation. So we were not too far off, I guess. Okay, so now it's time to look. Now it's time to look at this page 411. And page 411 is indeed a page on level 1. It's already at depth 1 inside the B+Tree. Okay, so indeed we are looking at an inner node now. And it has quite a number of live items, quite a number of index entries stored in itself. 285. One of these entries is indeed a high key, so we are let's disregard that. So it's 285 entries that is being stored here. So this is quite the fan out. It's in the range between 0 and 20, I would say. So 20 we have calculated as being approximately 500. The fan out 0 would be 250. So the fan out lies between that. That looks good to me. All right. So this looks plausible to me. That is an inner node that is packed to the expected degree. Okay. So we are indeed at level 1 now. All right. Root level 2. We are at level 1 now. One step deeper, and there is indeed on that level 1, the inner nodes are sequenced, are chained together using previous and next pointers, as the sketch on the slide has already indicated. Okay, so now let's also look at the index entries that we find in page 411, or at least at some of them. There's quite a number. Let's look at the first 10. Okay, so there you go. This is the first few entries inside this inner node. This again is the P0 entry. Of this inner node. All right, no key to be stored for the P0 entry. What you see here is high key information that we will disregard now. This is information about the sibling subtree that is being stored on the same level as the subtree we are currently looking at. So the child nodes that are being pointed to here by these index entries are indeed already leaf nodes. Recall we had a B+Tree of depth 2, root at level 2. We are currently looking at the node at level 1. These are child nodes or some of the child nodes of this inner node. They are at level 0. These are indeed already leaf nodes that are pointed to here. Okay, so let's check again the separator values so that we can check once we descend, for example, into the leaf node with number 288. This should be a leaf node. We will check in a minute. Then the entries on that leaf node should be equal to this value or larger, but less than this value. These are the two separator values that guard this 288 leaf node, or the child node in a sense in general. Okay, so let's translate that. right, that's 0198, 01985. All right, okay, forgot to cast to integer. Okay, and the other is 019A53. A53. Is this correct? These are hard to recall. And let's cast to integer. Okay, so now that we will descend into that leaf node, we are expected to find entries there, entries that represent rows whose values, a value is between these two minimum and maximum values. All right, this is the semantic of the search tree. All right, so then let's finally descend to the leaf level, 288. This is accessing the leaf node. Okay, and we find 367 entries there. One of these is the high key, so 366 usable entries on this particular leaf node page. So what we find here now is, let's go to the very beginning. There we are. Okay. So what we find here now is this is the first usable entry. Everything else is the high key entry. Okay, so this is the first usable entry, and this points into the heap file of the indexed table already. So on page 978 in slot 3.1, we will find a row value with this particular key value. Okay. We find a row with this key value. Let's convert that. And let's check whether we are in the expected bounds. Forget. So 104677, 104677. I think let's check here. This is indeed the minimum expected value that we were allowed to find or expected to find on this particular leaf page. The maximum value is this in decimal. All right, so let's check. This is the maximum value that we find. Okay. Just to check that the search tree structure is indeed intact. And all right. Oh yeah. It's 105042. That's less. That's one less than the exclusive border that we may not reach anyway regarding our search tree semantics here. Looks good to me. This is a B+Tree that appears to be just intact. So we now have made our way from the very top of the B+Tree, following the separators, used the separators to find the search tree, the search subtree that is of interest, descended into that search subtree, used the separators again, descended one more step, thereby reducing the size of the search space considerably, because we have a very wide tree, lots of pointers pointing out of such an inner node, until we reached the leaf level, from which we could, if we would wish so, travel into the data heap file of table index and access the wanted row. Looks good to me. All right, so much for the inner nodes and how PostgreSQL represents these inner nodes. It's really, as you can see, what you see on the slides is the true textbook style explanation of B+Trees, adapted a bit to match a PostgreSQL scenario. And indeed, PostgreSQL has an implementation of B+Trees that is really almost by the textbook. So this is makes PostgreSQL a really awesome system to study these really basic index and data structures in database systems. Okay, enough praise for PostgreSQL, more praise in the upcoming video. See you then when we have a closer look at how B+Trees are being used by the query engine to really efficiently evaluate predicates. All right, see you for that discussion in a few minutes. Bye.